A very good morning to every one of you. As has been said, I'm going to really be concerned about a link between graph theory, mathematical modeling, and drug design. And I'm going to point out some of the implications of our models to the discovery of new compounds for treating something called melanoma skin cancer. Well, maybe let me start by introducing myself. You know, there are some aspects in my life that actually shaped the way I do things, that actually shaped the way I think, that actually shaped perhaps some of my decisions. I grew up in a very poor rural area, and I was herding cattle, hunting animals, fishing, and of course working in the field. And these exercises actually taught me when to do things and when not to do things. One important thing that I was doing is basically assisting my grandfather, who was an indigenous medicine practitioner, and of course a healer. I would assist him as he did his practice, and this actually taught me to know some of the plants and herbs that can be used to heal certain ailments. And of course, in this rural area, people would not want their children to do mathematics because they would say, well, they will be taught simultaneous equations, and they didn't like that. But nevertheless, I went on to do mathematics, and I can share with you my first day at university. I told you that the rural area that I was in was very poor, and when I passed high school, when I had to proceed to university, the whole village came around and made contributions so that they can purchase an outfit for me. And that was done. That was actually my first day at university. And at university, I was worried with two things. Firstly, I was worried about my mathematics. And second, with my background, I was really very worried about the threat that we have to humankind, the threat that comes from diseases. So as I was doing my studies, undergrad, postgrad, PhD, and so on, research, I kept on thinking about how to help people with various ailments. But I was always asking myself, is there a link between maths and what I was doing? And for a very long time, I thought there was no link at all. But we will see how it progressed. So in the direction of diseases, I actually thought I could also practice, just like what my grandpa was doing. And the government actually gave me a practicing license. And so I started practicing, helping people with different difficulties, with different diseases. I actually used to practice at a center called the Herbal Clinic, and I would help a lot on Saturdays. And at Men's Phytomedical Center, men would come, well, nicodemously during the middle of the night, and I would also help them. Now, one would question and ask and say, what was the source of my knowledge and skills? Firstly, I said I was assisting my grandpa, and of course, I was also interacting with other experienced practitioners. And of course, as someone who can read, who can do research, who can write, my grandpa, well, would not read, would not write, but he was just using inherited knowledge. But the difference between me and him is that because I can do research, I can read, I can write. my additional source was actually coming from literature. So the question that we again ask is, but is that enough? Well, Cancer Association of South Africa mentioned recently that a common cancer in South Africa is a skin cancer, which we will learn more about in a few minutes, coming few minutes. They reported that every year we have about 20,000 cases, and we have about 700 deaths resulting from that skin cancer. Then we ask, how can those challenges be addressed? Of course, one would say we would desire to have drugs that can be used to cure or to treat skin cancer. But already we have challenges in drug design. As Hughes and his colleagues had it, they said generally drugs fail in the clinic for two reasons. First, do they work? That's one major concern. The second one is, even if they work, but are they safe? So drugs generally fail if they do not work or if they are not safe. And one measure of knowing whether a drug works or not is to use the numerical value associated with the drug or compound that is called the IC50 value of that compound. Loosely speaking, we are saying, what is the amount of the compound required in order to stop the spread of the disease or to inhibit it by 50%? But we will get to that very soon. Now, the drug development, the drug design process has quite a number of stages. But I'm very worried about the first few stages. I'm not sure if you can see clearly. We have the basic research stage, whereby the aim is to identify those compounds that can be used to manufacture the drugs. And that part of the research takes years and years. In my life, I've actually known two very notable researchers, one who is at a university here in South Africa, who has been looking for drugs that could cure malaria. He's actually in medicinal chemistry, and he has been doing it over the years, and he will design a new compound. He will think that it cures malaria. He will send to the laboratory. The laboratories will do the check, and they will tell him that, look, it's not quite there yet. And the next day, he will work on another compound, and he will submit it again to a lab, and they will again test and probably tell him that, look, what you had last year was actually better than what you have this year. And then the research continues. So you can see that it takes years just to identify the best compounds that can be used to manufacture drugs. And I have also known someone who unfortunately now is late, who used to go to the rural areas, and he will come back with a truck full of these plants and trees, and he would test them in the laboratory. So then the search is so expensive, and it's so difficult to quickly come up with a compound with the desired property. So these are some of the challenges that we get. So the question that we ask is, we have almost an infinite pool of compounds from where we need to identify the best compounds, our target compounds, which can work for certain ailments. So the question is, from an almost infinite pool of compounds, how do we identify? How do we identify? Well, some of you may say, but it's easy. Why don't we just go to a sangoma and perhaps we will be helped? And of course, to a certain extent, it works because these people are knowledgeable. But the question is it really good enough? Well, they've been around for years and years, and we continue to see quite a number of diseases which do not have drugs. So it's really not perhaps the best idea. Some may say, well, we can go to a prophet and the prophet can perhaps predict and tell us, look, this is what you want. Or this. But some of us would probably say, let's go for the laboratory work. Let's get the compound. We know it's 1 million and above compounds. Let's take them one by one into the lab and do tests. And once we have identified the correct one, we are good to go. So you would then see that the problem of going this route would involve burdens like high costs, and you also need laboratory experimental time. You also need human efforts. And one thing that I don't like, one thing that I seriously detest are the problems associated with animal sacrifice. If you are doing experiments with animal models, once you are done with your experiment, in most cases, even if they don't die, even if the animals don't die, you will end up killing the animals, even if they survive the test. The reason being that you want to check whether or not the vital organs were affected through the experiment. So these are some of the problems that come with. Now, just to give a formal definition of the inhibition concentration, that numerical value that we associate with each compound, that is an indication of how good the compound is in performing certain tasks. That is what we call the inhibition concentration, which is basically the quantity that one will need of the inhibitory agent in order to inhibit a certain biological process by 50%. Now, the question that myself and my collaborator, Professor Faranyabata from UJ, asked at some point was, can we predict the IC50 values, seeing that it's a numerical value? Can we predict it without going to the laboratory? Can we offer a fourth approach? Can we predict it without going to the laboratory? And we basically looked at each other, we smiled, and we realized that this was way too difficult. And we said, yeah, we think, because we are mathematicians, we think we can use mathematical models to predict the IC50 values. In other words, to predict the effectiveness of a compound in healing certain diseases. So the question was, how can we do it? Well, the starting point to our work was to say, why don't we go for something slightly less difficult? And then we thought that really looking at boiling points, which is a property of chemical compounds, we thought really looking at that is much more easier than the problem we were confronted with. So we sat down and we said, okay, let's consider alkanes. Why consider alkanes? Alkanes are chemical compounds that make up the bulk of mixtures in fuels. And these compounds are composed of the carbon atom and hydrogen atoms. And so, because they are always found in fuels, one would then say, knowing their boiling points would help a great deal in terms of, manufacturing the best fuel ever. But the question is, how do we get the boiling points of alkane chemicals? There are challenges. Determining them in the lab is expensive. And more so, in general, we've got lack of experimental data on boiling points. For instance, some even say because of inaccuracies of lab experiments, you get different values associated with as boiling points of different of the same alkanes or of the same chemical compounds, and that is usually a result of impurities, presence of impurities, and so on. So we then looked at each other again and we said, okay, how do we determine the boiling point without going to the lab? We said maybe we can use models to predict the boiling point. But again, the question is, yes, we have said we can use models, but again, the question is how? We looked at the literature. A lot was done, a lot was covered as early as 1947. That was being worked on by a PhD student then, Winner, who actually designed what we call the Winner Index, and so on. But then we noticed that some people tried this game, and researchers such as Nikolic and his colleagues in 1995 actually said, we are not sure how to answer this question because the structure boiling point relationship looks inferior. So we said, aha, we thought this is very easy, but it is not easy at all. So I then said to my collaborator, you know what, when I was about to get into second year, we were not so sure of which courses to choose until one of our classmates who had gone through a certain college said, well, guys, you need to choose a course called graph theory. Who does not know the graph of sine? Who does not know the graph of cos? But a very easy course. If we all join it, we will pass with flying colors. So we then registered for the course graph theory, thinking that we would start at the graph of sine, the graph of cosine, the graph of x squared, and our lives were going to be very easy. But in the very first lecture, we were told that, look, you think you know a graph, but you don't. A graph is not what you see on the screen. It's not that of cosine, it's not that of sine, but simply a collection of points which we call vertices when we get serious, and lines that join some of the vertices which we call edges. So I said to my collaborator, we have this area available to us, graphs. Can't we rely on that and probably get a foundation from there? And we read a bit about it, and we realized that actually in 1875, a lot of scientists and engineers got the wind about the importance of the chemical compounds called alkanes. And everyone then knew that these compounds were so important, very, very important. So they were then worrying and inquiring about how many are they. It's so good that we have them around, but how many are they? So most people would not be able to count them until Arthur Kelly, a mathematician, came into the ground and said, look, guys, I think I now know how to count alkanes. And he said, what I will do is I'm going to model alkanes, these chemical compounds, using what we call a graph. And I'm going to say each atom is represented by a vertex, and whenever two atoms are bonded, I'm going to represent that by an edge. So for instance, in the picture there, you can see a chemical compound, well known indeed, called quercetin, and alongside, you can see how it is represented by a graph. So that gave us a starting point. I also remember at some point in 2012, when my former PhD supervisor, Professor Dandelman, and I wrote a paper, there was a statement that Professor Dandelman included in the paper, and basically he said, if you look at graphs, distances in graphs, just studying distances in graphs is a very, very important thing. Why? Because it pervades all of science and mathematics and even our daily lives. Well, I did not know that that statement really is so accurate, and we are going to see some of the accuracies very soon. So perhaps because I'm going to talk more about that, let me just define the notion of distance between vertices in a graph. Suppose you've got a graph and you pick two vertices and you want to know the distance between them. All you do is you say, how many paths, how many routes do I have from the vertex, the first vertex to the last vertex? And you have your paths. And then you say, but I'm interested in being economic. I want a shortest path. Then you identify your shortest path, and then you say, what is the length of that shortest path? That then gives you the distance between any two vertices in the graph. And just a reminder, remember the problem that we were confronted with is, if I am given a chemical compound, an alkane, can I predict its boiling point? This is what we thought we would do initially, and once we are acquainted to the method, then we can get into drug design. Now, we then said, well, for us to be able to predict the boiling point of alkanes, we really need now having our graph as the representative model of our alkane. We now want to develop parameters that will capture some of the structural properties of the graph, and that can help us, that can play as a foundation to our model for predicting the boiling points. So the first parameter that we developed is something that we termed conduction of a graph, and it is defined basically as the sum of the scores of the vertices in the graph. And by a score, we were basically trying to simulate what happens if heat is moving from one atom to the other through the bonds. So that gave us the score of each vertex, that if a vertex has heat, how in general does it spread it through the entire graph? So we then developed what we called a score of a vertex, and that was basically the sum of the distances between that vertex and all vertices of degree 1 in the graph, and then we multiplied that by the square of the degree of the vertex. Well, when we say the degree of the vertex, we simply mean the number of edges that are incident with that vertex. And then the sum of the scores divided by the number of vertices in the graph is what we call the conduction of a graph. So for instance, if you look at the graph there in the screen, it's an alkane. It has 6 vertices, and one can actually calculate the conduction of that graph, and you will see that it's a numerical value. Its numerical value is 366 divided by 8. Now, what then do we do with that conduction, the developed conduction? So we then sat down and we worked on it very hard. And at some point we would say, oh, do you remember the behavior of the sine function? We know that a graph is not that of sine. We know that a graph is not that of cos. But this time around, we managed actually to merge the two. We then realized that, of course, through modeling, we then realized that whenever you have an alkane, you can actually obtain its boiling point by using formula number 1. So how exactly do you do it? You have an alkane A, represent the alkane as a graph, which is now a mathematical structure, and compute the conduction of the alkane, multiply by alpha, where your alpha is a constant given over there, 2.7173, add a constant beta, add a constant times log of your alpha 3 times the conduction plus alpha 4 base 2, and multiply that result by sine of that quantity which we can see on the screen. And we argued that actually that model predicts the boiling point of your alkane without going to the laboratory. So we tested the model. And if I am just to show you a snapshot of our results, you will see that the first alkane in that table is hexane, and it has conduction 15 that you can calculate using the formula. And it is known from lab experiments that its boiling point is 68.8 degrees. And our model says its boiling point is 68.8000222 degrees. And you can see the next one, the lab boiling point is 63.3, ours is 63.299, and so on. The next one, 60.9, ours is 60.90011, and so on. So when I was talking with my research collaborator, he then said, well, we can actually give an assessment of that model, and we can associate that with the COD value, the coefficient of determination, which is R squared value. It's actually having R squared value, which is pretty good. But he told me that, you know what, my entire life, I was dealing with models. And this is my first test of real meat from mathematics. You can see the accuracies of the model. So I have not forgotten that we want to talk about drug design. So I'm now going to get back with that foundation, to get back to skin cancer. Well, we've got melanin, which is a natural pigment made by special skin cells called melanocytes. And this melanin actually provides a defense mechanism against the sun. And it also determines the color of our skin, the hair, the eyes, and so on. And it's produced in the body. But its production is actually catalyzed by an enzyme called tyrosine. So this enzyme is quite crucial. But unfortunately, if the enzyme works terribly hard, that results in the overproduction of melanin. And that actually, the overproduction of melanin leads to what is known as melanoma skin cancer. So in all this business, we then worry about, can we develop drugs that can reduce the production of melanin by inhibiting the activity of our tyrosine? So we are targeting that enzyme, and we are saying, you are working far too hard to our liking. So we want to ensure that we inhibit some of your activities, and then we will be able to control our skin cancer. And of course, the effectiveness of inhibiting the enzyme is measured in IC50 values. There were some researchers who were also very worried about identifying such drugs. And that's Suwan and his colleagues. They said, well, we have obtained a grant, we have obtained some money, and we can buy some chemical compounds. We can take them to the laboratory, depending on our budget, and we can test their effectiveness in inhibiting that enzyme. And they did so. They took some flavonoids. Actually, they took 9 of some flavonoids. That is as far as they could go. And they did test, and then they got as their best compound quercetin with an IC50 value of 96. So you can see that some of the compounds are actually performing worse off than quercetin. Here their best was quercetin. So then they announced to everyone and said, we went into the laboratory with these 9 compounds, and our best emerged to be quercetin. But unfortunately, we no longer have money to continue, looking for, because even quercetin is not good enough. That is what it does, but it's not good enough. So hey, this is what we have. These are our results. So with my colleague, we then asked, can we predict the effectiveness, in other words, the IC50 values of all the other flavonoids? And we then said, well, if you look at these IC values, these are numerical values, and that then lies within the domain of mathematics. And on the other hand, we then said, but we have compounds, and these are graphs, so those are also mathematical structures. So we said, so we have two things here. One, on one side, a graph, which is a mathematical object. On the other side, a numerical value, the IC50, which is a mathematical object. So we said, let's go ahead, let's see if we can use mathematical models to do that. Then again, the question was, but how? But how? We then realized that we cannot achieve that easily, but we needed more machinery. The first thing that we recalled is that sometime, some years back, there was a parameter that we introduced in graph theory for the sake of studying graph theory that we called irregularity index. And of course, there are also other parameters in graph theory, such as the eccentricity of a graph. We combined all that, and we then developed a new parameter based on two sister parameters, one known as the external activity of a graph, and the other one known as the internal activity of a graph. Basically, we were saying what happens outside the church would probably differ a lot from what happens inside the church. So we put those two together, those two variables for each compound or graph together, and we used those two to develop a model that can predict the IC50 values of flavonoids. So our model is a function of two variables, the variables being the internal activity and the external activity. So what then it means is that whenever you are given a chemical compound that is a flavonoid, represent it by way of graph, calculate its internal activity, calculate its external activity, put them, substitute them in formula number 2, which is our model. And what you get is actually the effectiveness of that compound in treating melanoma skin cancer. So we started off with a chemical compound, represented it by a graph, computed the graph parameters, put it in a mathematical modeling formula, and get the effectiveness of that compound in treating melanoma, in inhibiting the enzyme tyrosinase. And that model actually has a COD value of 1, which is really great. So for all purposes, one can then use that model to say, okay, can I look at all the other compounds that are there, that are flavonoids, and predict their effectiveness? And can I then rank and select the best? We actually applied that model, and we did that. We were so happy that our model actually managed to identify troponin to be 13-fold stronger than quercetin. Remember, quercetin was actually identified among those 9 as the best compound. So our model identified troponin to be 13-fold stronger than quercetin. Why troponin? Troponin is actually a well-known standard anti-skin cancer drug agent. Now, apart from that, our model discovered 8 more compounds that are stronger than troponin, which is a standard anti-skin cancer drug agent. And very interestingly, among the 8 compounds, There is compound A, which is actually 34-fold stronger than propolone. And also, more interestingly, compound A is actually commonly used for bodybuilding, treating anxiety, inflammation, gout, and ED. So what we are now thinking of doing is to ask our collaborators to take this compound A into the laboratory and to do tests to verify that indeed compound A performs in a manner that the model says it performs. And that, of course, is called preclinical trials. Thank you very much for attending my talk. Thank you, Chair. This marks the end of my talk.
Thank you very much, Prof. Simon, for a very interesting talk. And good luck with compound A, the future of compound A. Now, are there any questions? And Floyd, you must please help me if I don't see a hand. Are there any questions?
There is a hand. We'll start with the floor because we have hands on the floor, so we'll start with one
Is there a hand? Who is it, Floyd? Okay, please guide me there, Floyd.
Yes, they will speak now.
Yes, my name is Darison Irenda from the School of Mathematics. Now, if I look at the IC50 values, is there a maximum or a minimum? Concerned about the range.
Yeah, that's a very good question. Let's look at what it does. So the IC50 value is simply a measure of how much of the substance you need to administer so that you can treat by 50%. Now, sometimes it may be very, very small. If it is very, very small, it shows how effective that compound is. You just need a little bit to make a person okay, right? But if your IC50 value is, say, buckets and buckets and buckets of the compound, then that shows that the compound in question cannot do the job. Yes. So mathematically, we of course don't have an upper bound, but of course the lower bound will be there, yeah, as your zero. But of course, when it comes to drug design, usually they will say, well, any compound whose IC50 value is higher than this, we discard, we don't consider because we assume that they don't have activity.
Yes, I'm Manfred Möller, also from the School of Mathematics. Thanks, Simon. It was a great talk and very motivating. And of course, now the work actually starts to see if your model is useful, because I realized you had in your last formula 9 parameters. And I assume you took these 9 compounds before to adjust these parameters. And now it would be, of course, great mathematical intuition if that formula would actually very well predict. But these preclinical trials and other trials, if it works, would, of course, need a lot of collaboration and monetary input, let's say. But I wish you good luck with that. But it also shows that how some of these very abstract mathematical objects in graph theory come into something which has then later practical use. So it actually shows how important it is also to do mathematics just for mathematics' sake. One never knows what the application later may be. For example, about 100 years, Hardy was very proud to do some mathematics which is not applicable. And now we know how applicable that mathematics he was doing at that time with coding. And I wish you good luck with that, and that it will also be very applicable what you're doing.
Oh, thank you very much. I am humbled, and I'm sure all my collaborators are so happy to hear those words. For a very long time, I did not know that we are sitting on gold. Yes, we can actually use mathematics to help design drugs which we can hold in our hands and put in our mouths. Thank you. Thank you very much.
Okay. We have another question on the.
Thank you, Prof. Manfred. Simon, I have Rihanna. Rihanna, you have a question? Oh, no, it's Eric. Apologies, it's Eric and not Rihanna.
Yes, hello everyone. Thank you for this nice talk. I have one not important comment and one technical question. So what I was saying is maybe one can see the graph of a function as a special case of graph in graph theory, because if one think about it, a graph of a function is a set of some dots, some of which may be connected. Yeah, so maybe those are special cases, and in graph theory you do more general. Anyway, the technical question is in the definition of a score. You say the end vertices. S is a set of end vertices. Are those? Does that mean some special kind of vertices, or is any vertices the end vertices?
Usually when you have your graph, you would worry about the following. I'm going to consider the graph in the picture. You would worry about the number of other vertices that a vertex is joined to. For instance, your vertex V is actually joined to W, and your vertex Y is joined to U, W, and to Z. So you can see that Y is more popular than V in a sense. So that parameter, which tells us the number of vertices that a vertex is joined to, is called the degree of the vertex. So the degree of V here is 1 because V is joined only to W, which is one vertex. The degree of Y is 3 because Y is joined to 3 other vertices. Now, of special interest are those vertices that sit in the graph that behaves like outsiders. They have only one link, unlike everyone else. So these vertices are vertices with degree 1. For instance, in the picture, your Q and your V are vertices of degree 1. They are kind of outsiders. They are kind of external vertices. But all other guys there with degree bigger than 1 are known as internal. So the set S is the set consisting of all those external guys, consisting of all those vertices of degree 1. So that is the set of outsiders. And we consider those separately from the insiders, because the roles they play are different.
All right, we have one more question on the floor.
My name is Ben Mahoud from the School of Mathematics, and thanks for the talk.
Okay, great.
Should I continue? Yes. So can you go back to your last slide? I don't know if maybe I missed in the presentation, because there is a point where you say among the A, compound A, which is the 4-fold stronger than tropolon. What is compound A? Maybe I missed it. But I was wondering, like, we need to know this compound. I mean, is that the force stronger than tropolon? perhaps it might be quite helpful.
Yes, before doing the research, we also wanted to find out what compound A was. But let me put it to you this way. You see, the world that we live in, you can imagine if Coca-Cola had gone out in the open and said, you know what, for you to manufacture Coca-Cola, you need to take compound A, which is exactly this, put it together with compound whatever, put it together with this other, and then you have your what? Your Coca-Cola. I'm sure Coca-Cola was not going to benefit out of that creation. Because then everyone in the street would, run around and also create some. So there are issues here to do with intellectual property and so on. So this is why we have kind of suppressed naming explicitly what compound A is. Yes. I know my research collaborator will kill me. I'm joking.
I know it.
I think she seems to be having some. Still have one.
No, but since the formulas out in the open, and so you just need all your compounds you can find and calculate the corresponding values, substitute in the parameters, and you get a compound A.
Exactly. Actually, with some hard work, once the formula is accurately, so accurately put in the oven, you will be able to do that. But it may happen that we change a bit. This is for presentation purposes. Yes.
But you did it with the first example, you actually put in the values. These
Yes,
examples, you
for
did
the
not
first
put in
one
the
is-
values of
yes,
the parameters
yes,
in your presentation.
Yeah.
So apparently we are still looking for, later we will know the 8 more compounds. And then from the 8 more, we know which one is the compound A. That's what we are saying.
Actually, those 8 compounds, we ranked them already.
Okay, it's already
Yes,
done.
they are ranked already. But then we just took the best out of the what?
The 8.
The best 8, yes.
So the 8 is not among the ones the previous all guys
No.
considered. Yeah.
No, they are new ones.
Okay, I think we still have more questions on Zoom for those who are joining us via Zoom. And then if that's the case, that there are no more questions, thank you everyone for joining us today. See you next week on the next seminar. Thank you.